This video we're going to be looking at data visualization concepts. So for this, I've picked 3 chapters from some reading I've been doing, and I thought it's very useful. So I'll just analyze what I've read. So chapter 6 of Rules of Thumb in Tamara Monsner's Visualization Analysis and Design. She talks about, or the author talks about, I actually don't know if it's a he or she, talks about no unjustified 3D. So when to use 3D? Only when the user's task inherently involves understanding the shape of 3D structures, for example, fluid dynamics, medical tomography, or molecular structures. No unjustified 2D as well. So 1D list versus 2D layouts. Lists, the author argues, offers much higher information density and faster lookup times when sorted, whereas when to use 2D is laying out data in 2D space like node link graphs, should be justified by tasks requiring topological understanding. Otherwise, structured 1D lists are often superior. So this diagram contrasts. So the author argues that on the left is much better for viewers trying to synthesize data than 2D layout, which is often only used for comparing the dynamics between, in this case, clusters, bridges, gateways. Just take a moment to just analyze this as well if you want. Now moving on to the next point. So means the user needs to analyze the network structure or relationships in the data set. So one-dimensional uses a single spatial axis to arrange items along a linear path. So even though, of course, this is 2D, but it's one-dimensional in terms of spatial axes. So the core advantage is maximum information density and fast lookup speed. It's best for sorting, ranking, and direct comparisons. Examples include sorted lists, tables, standard bar charts, and timelines. Two-dimensional uses 2 spatial axes, x and y, to position items across a plane. So the core advantage is that it reveals complex spatial relationships, correlations, and network structures. It's best for analyzing multivariable trends, clusters, and connectivity. Examples include scatter plots, network node link diagrams, and maps. The author argues that eyes beat memory. So cognitive load, human working memory, and attention are extremely limited resources. Externalizing information on screen reduces the need to track or recall previous views. So animations versus side-by-side views. Animated transitions help maintain context across simple changes. Multi-video frame playback, rather. I'll say that one more time. Multi-frame video playback of complex data forces reliance on memory and often causes change blindness. Small multiples, side-by-side views of discrete states are generally more effective for detailed comparison tasks. So I thought this was very useful as well. So for example, if you're playing a video, the human brain doesn't process it as well as if you took screenshots of the key information you wanted to demonstrate and just present it as slides. So like this is slide 1 is showing this, slide 2 is showing this. Resolution over immersion trade-off. Immersion VR setups sacrifice pixel resolution and spatial density for a sense of presence. This is a bit more expert level because not many people even would have access to VR setups, but maybe in the future VR setups get so advanced that it kind of counteracts this author's opinion. But for now, the author also argues that immersive hardware isolates user from standard tools like keyboard, mouse, secondary apps, and causes physical fatigue. The guideline is maximizing pixel resolution on desktop displays is almost always more critical for abstract visualization than creating an immersive environment. The next one is overview first, zoom, and filter, details on demand. So overview provides broad awareness and summary of the entire dataset without requiring initial navigation. Zoom and filter allows users to reduce the dataset to explore areas of interest. Details on demand displays fine-grained attributes when selected. Alternative for massive data, search, show, context, expand on demand is better suited when top-down overviews are non-viable due to extreme scale. Responsiveness is required. So the interaction design must respect human perception latency classes. So perceptual processing takes 0.1 seconds. Smooth screen updates and frame animation. Immediate response is normally within a second. So confirming an action, for example, mouse selection, hover, or visual feedback for that. And then brief task is normally around 10 seconds, completing small discrete interaction steps without losing focus. So another key concept is to get it right in black and white first. So crucial visual information must remain legible when converted to grayscale. So channel hierarchy, map the most important visual attributes to luminance, brightness to guarantee adequate contrast, preserving hue and saturation for secondary encoding. So this comparison clearly shows what the author is trying to illustrate. See, in grayscale, you can still read everything clearly. So you're still able to convey what you want to convey. However, now that you've added color and luminance, it just sort of further illustrates the points that you would try to convey if you're talking about this diagram. Function first, form next. So a functional yet aesthetically plain design can be progressively refined into a beautiful display. An ineffective design, no matter how visually appealing, must usually be discarded entirely. Visual beauty enhances usability and engagement. Aesthetics should refine function rather than dictate it. Cool. Moving on to chapter 5 from Scott Murray's Interactive Data Visualization for the Web book. And it talks about what is data and web formats. So data is structured information with potential for meaning. D3 supports formats, for example, supported formats rather. For browser-based visualization with D3, text-based formats are used, for example, plain text, comma-separated values, and tab-separated values, or JSON as well. Binding requirement, data cannot be visual or useful in D3 until it is attached, bound to page elements. Just take a pause and have a read through this table as well. I'll just zoom out a little. Generating page elements and method chaining. So elements like P, rectangle, circle are added dynamically to the DOM to represent data points. Chain syntax. Actions are linked together with periods to execute sequentially in a single expression. So dot select body finds and returns a reference to the DOM element matching the selector. Append P creates a new element inside the selection and passes a reference down the chain. Text inserts text into the newly created element. Execution order. Method order is critical. Each method's output must match the expected input of the next method. So just as well for your understanding, DOM stands for Document Object Model. It is a programming interface for web documents like HTML, XML, or SVG, representing the page as a hierarchical tree structure of nodes and objects. This model allows programming languages, most commonly JavaScript, to access, traverse, and manipulate the structure, style, and content of a document in memory. In the DOM, each element, attribute, and piece of text is represented as a node. The root node is typically the HTML element with child nodes like head and body. This tree-like representation enables developers to dynamically update parts of a page without reloading it. So moving on to data loading methods. So CSV loading, D3 CSV, a synchronous function that executes a callback once the file finishes downloading, reads headers as object key properties and rows as values. Old values are loaded as strings by default, requiring type conversion for numbers. Row conversion, pass a converter function, e.g. using passFloat, to pass strings into numeric values during loading. Asynchronous handling and scope. External data is only guaranteed to be available inside the callback function. Always reference loaded data within the callback or store it in a global variable for subsequent functions, and includes an optional error parameter, function error data, to safely catch network or missing file errors. And don't worry, I've done a demo for this as well, which will be at the end of the theory. Other loaders, D3.tsv for tab-separated files and D3.json for JSON files function with identical callback structures. So binding data to DOM elements, data method passes the dataset array and it determines how many iterations to execute downstream. Enter method compares the data array with the current DOM selection. If there are more data items than existing DOM elements, enter creates placeholder elements for each missing item. Memory storage, when bound data is stored in the memory as __data__ attribute on the DOM element object, confirmable in the browser console. Next, we have using bound data with anonymous functions, so accessing data. Once bound via data, D3 methods like .text, style, .attribute can take an anonymous function that receives the current data B as input. So if you read this JavaScript, for example, and then dynamic logic and styling. And just to clarify, datum stands for a piece of information or a fixed starting point of a scale or operation. Dynamic logic and styling functions can evaluate expressions or conditions based on D. Example, changing text color conditionally based on a threshold D greater than 15 using style color function D. And I do this in the example demo as well, coming up shortly. Final chapter is chapter 6, again it's called Drawing with Data from Scott Murray's Interactive Data Visualization for the Web. So drawing bar charts with HTML divs. So atch versus style. Attribute sets HTML attributes directly on elements, for example, attribute class bar. Style applies inline CSS property directly to elements, for example, height 75 pixel. Class toggle, so class, use class bar true or class bar false to add or remove CSS classes quickly. Data-driven height, set height dynamically by returning pixel values from an anonymous function. So for example, .style height function return d times 5 plus px. And again, this is explained in the demo. Dynamic datasets and generating random data. So automatic looping. The data method loops through datasets of any size, updating the context. So D always refers to the current datum in each iteration. Random data generation. Use standard JavaScript loops to populate datasets dynamically. Math.random returns a decimal from 0.0 up to, but not including 1.0. Math.floor, math.random max rounds down to yield clean whole numbers and integers. So drawing SVGs and data-driven shapes. So this is very important. SVG canvas setup. Store the SVG container reference in a variable using defined dimensions, width and height to simplify downstream positioning. In this example here. Index parameter, D3 automatically passes the element's numeric index as the second argument in callback functions. And horizontal positioning, use index I to space shapes evenly across the canvas. Making an SVG bar chart rectangle, so flexible coordinate scaling, bar position x equals to I times y, w divided by dataset length, ensures bars scale horizontally regardless of data length, and bar width, w divided by dataset length. Bar padding adjusts individual column width dynamically. Overcoming SVG coordinate origin, top left. SVG coordinates are at 0, 0 in the top left corner, meaning shapes grow downwards. To make bars grow upwards from the bottom edge, set y to the canvas height minus the data value. Color encoding and value labels, data-driven color dual encoding. Visual properties like fill can be derived dynamically from D, for example, RGB 0, 0, math.round D times 10. So the greater the value of D is times 10, it gets assigned a different R value. So most times, for example, like what I do in the demo, the greater the value, the more striking or luminescent the color blue is, for example, which highlights change. So it's very good for data visualization. Adding SVG text labels appends text elements mapped to the same data array. And label alignment, use text anchor equals middle combined with an X calculation offset by half the bar width to center value labels perfectly inside columns. And then creating scatter plots, 2D data. Nested arrays, 2D data points are represented as multi-dimensional arrays, for example, 520, 480, 90. where D0 accesses the X value. For example, in the first one would be 5, and D1 accesses the Y value, so that'd be 20. Circle size encoding rule. When mapping quantitative values to circle size, always map data to circle area, never to radius. Reasoning is that mapping directly to radius distorts relative proportions visually over representing largest values. The formula, since A is equal to pi r squared, calculate radius as square root of area divided by pi, or simply radius is equal to the square root of the data. And all this will be in action very shortly as I go through the demo, but this is the theory section, and thank you very much. So here is a demo of the first breakdown in action. So what we're trying to achieve here, the big picture, is the core of this exercise is to demonstrate data-driven DOM manipulation. Instead of hard-coding standard HTML elements like p tags into our code, we use D3.JavaScript data-driven documents to bind raw data, an array of numbers, to the web page, dynamically create HTML elements for each item in that array, control visual encoding, text content, and CSS text color based on conditional rules in the dataset. So the code walkthrough, how the parts relate. So part A that I want to talk about is importing D3, which is script src example that I've highlighted just now. This loads the D3 library version 6 into the browser via CDN, so we have access to the global D3 object and its method chaining API. Then defining the raw data, we have variable dataset equals to these values. This represents raw input data, in this case 5 numerical data points representing daily cat video counts in this example. Now the core D3 pipeline is this section here that I've just highlighted. And how it works is the body part selects the target parent container in the DOM where elements will be injected. The select all P tells D3 to look for existing P elements. Since none exist yet, it returns an empty selection. Dataset passes dataset length 5 and binds each array value to an element slot in memory. Then we have enter, which identifies the data points that do not yet have matching DOM elements, in this case all 5 elements. It creates placeholder nodes waiting to enter the document. And then append P takes those 5 placeholders and physically injects concrete P tags into the DOM inside body. Now we have data-driven content and styling. So the text function D, etc. This bit here. D3 loops through each bounded element. The anonymous function accepts D, the raw value for that specific iteration, for example, 14, 5, etc. Logic values, if D is greater than 10. So if true, it pretends warning to signal high viewership. Otherwise, it outputs a standard statement. Then we have the style color function, for example. This modifies the inline CSS color dynamically. Values above 10 turn red to visually draw user attention, a foundational concept in visual hierarchy and warning indicators. And then DOM verification is this bit here. So this logs the updated D3 selection to the browser DevTools console so that you can inspect the underlying __ data _ property attached to each P DOM element. When I say P, it's less than symbol P greater than symbol, like how you would write a paragraph normally. And then, yeah, that's pretty much it. And on the right, we have what it looks like in practice. Moving on to the second lab, in this task, what we're trying to achieve is we bound data to basic HTML paragraphs. In task 2.2, which is this one, we transition to true visual data visualization by rendering graphical primitives inside an SVG, scalable vector graphics container. Instead of text blocks, we use D3 to map numerical values directly into spatial geometries. So data value could be rectangular height, an array index could be horizontal X positioning, and data value could be the color, intensity, and label placement. So just for the code walkthrough, this section here is setting up the canvas variables. So it establishes dimensions for our SVG canvas. Bar padding leaves a 1 pixel gap between rectangles so individual bars don't merge into a single solid block. And then creating the SVG container is this bit here. So it selects the body elements and injects an SVG tag with a hard-coded width of 500 pixels and a height of 100 pixels. The variable SVG holds the container so we can append graphical elements directly to it. So drawing the rectangles, we have this video. So just like paragraph binding, this selects all non-existent rectangle tags, binds the 10 data points from dataset, creates 10 placeholders via enter, and appends rectangle elements into the SVG. Horizontal position. which is, yeah. So W divided by dataset dot length, 500 divided by 10 equals to 50 pixels per bar, multiplying by index I, positions each bar evenly across the axis. Bar 0 starts at 0 pixel, bar 1 at 50, bar 2 at 100, for example. So flipping the SVG coordinate system Y is this next bit. Essentially, standard web coordinates place 0, 0 at the top left corner. If Y were to set 0, bars would go downward from the top ceiling, which is not generally how we read bar graphs. So to fix this, we make bar graphs grow upwards from the bottom. We calculate h minus bar height. For example, if a bar is 56 pixels tall, 14 times 4, setting Y is equal to 100 minus 56 equals to 44, places its top edge 44 pixels from the top, pushing its base cleanly against the bottom edge. Width and height. So this sets width to the calculated column width minus padding. So 50 minus 1 equals to 49 pixels. Sets height dynamically scaled by a factor of 4, d times 4. So small values like 5 remain visible, while large values fit within the 100 pixel canvas height. Color coding, build. So dynamically constructs an RGB string where the blue component scales with the value d times 8. High values yield brighter, vivid blue colors, while smaller values appear nearly black. So this is a pretty smart way of doing this. Adding precision data labels. So this binds the same dataset to an enter pipeline to append text nodes over top of each bar. Essentially the numbers. And the final bit is the label alignment tricks. So horizontal centering, setting text anchor to middle, sentence text around this x coordinate, adding half the bar width, 50 minus 1 divided by 2, with 50 minus 1 being in brackets, is equal to 24.5 pixels, places the anchor point dead center inside each rectangle. And then the next line, is places the text baseline 14 pixels below the top edge of each bar. So numbers sit neatly inside the bar rather than floating above it. And then all this gives you what we have on the right. So for this next task, what do we try to achieve here? We try to upgrade to multivariate 2D data to build a scatter plot. So instead of mapping single numbers, we work with an array of coordinate pairs, x, y. Each pair is represented visually as an SVG circle element placed dynamically on a 2D Cartesian plane. We use conditional color highlighting to draw attention to specific outlier data points. So working with this data set here, instead of a simple array of numbers like 14, 5, 26 like we had before, the data set is an array of sub-arrays. In D3 callbacks, D represents the entire inner array. For example, 520. D0 would be the x value, 5, and D1 would be the y value, e.g. 20. So drawing circles is this section here. This binds the 10 coordinate pairs, creates 10 placeholders via enter, and appends circle tags to the SVG canvas. This bit that I've just highlighted now, unlike rect, which uses top left x, y corners, circle elements are positioned using cx, center x, and cy, center y. Here, D0 maps directly to cx, and D1 maps directly to cy. Radius r is here, it's 5, it's a fixed radius of 5 pixels for every data point. This section here scans each data pair's x value. If the x value equals 480, the maximum point on the far right, it fills the circle in red to highlight it as an outlier key data point. All other circles default to slate gray. You can see that in this example here, there's only one variable data point that's red because it meets that requirement. So adding data labels, use a string concatenation to form the subarray numbers into readable coordinate label, e.g. 520. as you can see in these examples here. The next bit here shifts the label 8 pixels to the right of the circle center so the text doesn't render directly on top of the dot. And the vertical shifts the text down slightly so it's baseline aligns vertically with the center of the circle. You can see how the values are what we would say to the right of the dot. And yep, that's it for this task. Now on to the final lab. So what we're trying to achieve here is we step into real-world web development by asynchronously fetching data from an external file. So the key achievements in this lab is asynchronous data loading, fetching external CSV files using D3.csv, converting text strings into numeric data types using the unary plus operator, modular JavaScript, separating HTML structure, index HTML from application logic, lab4.js, and wrapping execution inside window.onload equals init, semicolon, targeted DOM insertion, using D3 select chart to place the visualization precisely above the footer, rather than appending it blindly to the body. So working through the code, in index.html, we have a modular HTML structure. So we load the D3 first in the head, so the D3 global variable is defined before lab4 JavaScript executes. And then we have the target container chart. Adding IP ID equals to chart allows us to bind our SVG directly to a specific placeholder rather than appending it to the bottom of a body below the footer. So now into the JavaScript. We have the function init and window.onload equals init. So that's at the very start and very end of the JavaScript. So why window.onload? Because our script is loaded in the head before the DOM element exists. Running code immediately would cause D3.select chart to fail. Window.onload equals init guarantees the browser finishes parsing the HTML before JavaScript tries to manipulate chart. Then we have the asynchronous CSV fetching and type conversion. Just here. So the D3.csv returns a JavaScript promise. Because fetching network files takes time, D3 operates asynchronously, fetching the file in the background and executing .then only after the download completes. String parsing plus d.wombats. CSV files store all values as text strings, e.g. 14. Placing the plus operator before d.wombats casts the string into a numeric integer float, 14, preventing mathematical bugs during coordinate calculations. Dynamic chart rendering. All this video. So the D3.select chart specifically attaches the SVG canvas inside ID equals to chart, fixing the layout issue where charts accidentally render under footers. Property access d.wombats. Since CSV rows are passed into objects, wombats 14, we access values using dot notation, d.wombats rather than basic array indexes. So in case you guys were wondering where I got these values from, I got these from creating the Excel spreadsheet, so that's where 14 is, for example, and all these values get passed through. But to continue on, we have dynamic chart rendering, or the bar chart. So dynamic color scale is the next function that we're going to talk about. So in this bit here, this scales the blue channel dynamically based on the d.wombats times 10. Math.min 255, caps the value at 255, so RGB calculations never produce invalid values. And that is it for our demos. I hope you enjoyed this video, and I'll see you in the next one.